For most of human history, we looked up at the night sky and assumed it was fixed, eternal, and unchanging. The stars seemed to hold their places, the planets followed their paths, and Earth felt like the stable center of everything. But over centuries of discovery, we learned that this was an illusion. The Earth spins on its axis and races around the Sun. The Sun itself is in motion, orbiting the center of the Milky Way. Our galaxy, once thought to be the entire universe, is only one of billions, and it too is moving, pulled by vast cosmic structures we can't even see with the naked eye. On the largest scales, space itself is expanding, carrying galaxies farther and farther apart. So the universe is not static, everything is moving, from the smallest atoms to the grandest galaxies. And that raises one of the most profound questions we can ask: where is everything in the universe going? In this video, we'll take you on a journey through 10 chapters, from the first illusions of a still cosmos to the discovery of galactic motion to the ultimate fate of everything. But before we dive in, if you enjoy exploring the mysteries of space and time, make sure to subscribe, hit the like button, and ring the notification bell so you don't miss future episodes. And if you find this video thought-provoking, share it with someone who loves the cosmos as much as you do. Now let's begin our journey with Chapter 1, the illusion of stillness. When we look at the night sky with our own eyes, it appears calm and unchanging. The stars seem fixed in place, the constellations repeat their familiar shapes, and the motions of the sun and moon follow a predictable rhythm. Over the course of a lifetime, the sky looks the same, giving the impression that the universe is permanent and unmoving. To ancient civilizations, this appearance wasn't an illusion, it was reality. With no telescopes or scientific instruments, they relied on what the human eye could see, and what it saw was stability. Because the ground under their feet felt solid and the heavens appeared to rotate above them, the logical conclusion was that Earth was at the center of everything. This geocentric worldview became deeply rooted in cultures across the globe. The Greeks, Egyptians, Chinese, and Mayans all constructed cosmologies that placed Earth at the center. One of the most sophisticated versions came from Claudius Ptolemy in the 2nd century CE. Ptolemy built on centuries of astronomical knowledge to develop a model in which Earth sat motionless at the center of the universe, surrounded by concentric spheres that carried the moon, the planets, the sun, and finally the stars. The stars were thought to be fixed on a great outer shell, which rotated once per day to account for the rising and setting of the sky. Ptolemy's model wasn't just speculation, it was a mathematical system that allowed astronomers to predict planetary positions, eclipses, and seasons with surprising accuracy. It introduced epicycles, small circular motions superimposed on larger orbits to explain the strange looping behavior of planets like Mars. For more than 1,000 years, this Earth-centered model remained the dominant scientific truth. For people living in that era, the system wasn't only about science, it also provided comfort and order. If Earth was the center, then humanity occupied a privileged position in the cosmos. Religious and philosophical systems embraced this idea, presenting the universe as a carefully designed structure with Earth at its heart. The apparent stillness of the sky was seen as proof of divine perfection. The idea of a dynamic, constantly changing universe would have seemed absurd and even threatening. But cracks began to appear in this picture. In the 16th century, Nicolaus Copernicus proposed a radical alternative. He suggested that the sun, not Earth, was at the center of the system. Earth, he argued, was simply another planet, orbiting the sun along with Mercury, Venus, Mars, Jupiter, and Saturn. In Copernicus's model, Earth also rotated on its axis once per day, explaining the daily rising and setting of the stars. This heliocentric model simplified some of the awkward aspects of the old geocentric system, but it was difficult to accept. After all, people did not feel as though they were spinning or moving through space. And if Earth were really in motion, why didn't the stars appear to shift their positions against the background sky? These questions made Copernicus hesitant, and he only published his work near the end of his life. The real turning point came in the early 17th century when Galileo Galilei used a new invention, the telescope, to study the heavens in greater detail. Galileo discovered craters and mountains on the moon, showing it was not a perfect, divine sphere. He observed 4 moons orbiting Jupiter, proving that not everything revolved around Earth, and perhaps most importantly, he saw that Venus went through phases like the Moon. These phases could only be explained if Venus orbited the Sun. This was direct observational evidence in favor of the heliocentric model. At the same time, Johannes Kepler, using the careful data collected by Tycho Brahe, worked out the true path. After years of calculations, he discovered that planets move not in perfect circles but in ellipses, with the Sun at one focus. This insight removed the need for Ptolemy's complicated system of epicycles and explained planetary motion with much greater accuracy. Isaac Newton built on this foundation later in the 17th century. By formulating the law of universal gravitation, Newton showed that the same force pulling an apple to the ground was responsible for keeping the Moon in orbit and the planets circling the Sun. His mathematical laws unified the heavens and the Earth under a single framework. For the first time, people understood not only that Earth was moving, but also why. The illusion of a still cosmos had been decisively overturned. Yet even now, centuries later, it still feels like we are standing still. We don't feel the Earth spinning beneath our feet at more than 1,600 kilometers per hour at the equator. We don't sense that our planet is orbiting the Sun at 107,000 kilometers per hour. We don't notice that the Sun itself is moving around the center of the Milky Way galaxy at over 800,000 kilometers per hour. From our perspective, the world is stable and unmoving. The reason is simple: motion is relative. When you are in an airplane cruising smoothly, you can walk, read, or eat as if you were sitting at home. It is only when turbulence or sudden changes occur that you feel motion. Earth's motions are constant and smooth, so we feel nothing. To us, the illusion of stillness persists, but the reality is very different. Right now, as you read this, you are on a planet spinning once every 24 hours, orbiting the Sun once every year, riding along with the Sun as it orbits the Milky Way once every 225 million years, while the entire galaxy itself drifts through space, pulled by larger cosmic structures. We are moving on every scale imaginable. The calm sky above us hides a universe in constant motion. The realization that the universe is dynamic rather than static completely changed our understanding of reality. It shifted our place in the cosmos, from the immovable center to just one participant in a vast, evolving system. This new perspective laid the groundwork for all of modern astronomy. It also opened up new questions. If everything is moving, where exactly is it all going? What is the destination of this motion? And what does it mean for the ultimate fate of the universe? Those questions will guide the rest of our exploration. What began as an illusion of stillness leads to one of the greatest scientific investigations in history: the search to understand the motion of everything in the universe. For thousands of years, Earth was seen as the immovable center of the universe. The geocentric model, supported by Ptolemy and deeply integrated into religion and philosophy, placed our planet at the heart of all celestial motion. To people at the time, this made perfect sense. The Earth felt stable beneath their feet, while the Sun, Moon, and stars clearly seemed to circle above. But by the 16th and 17th centuries, evidence began to accumulate that this view was wrong. The revolution that followed would completely remove Earth from the spotlight. The first major step came from Nicholas Copernicus, a Polish astronomer and mathematician. In 1543, near the end of his life, he published On the Revolutions of the Celestial Spheres. In this book, he presented a daring idea. The Sun, not Earth, was at the center of the cosmos. Earth, he argued, was just another planet orbiting the Sun, completing one revolution every year. He also proposed that Earth rotated on its axis every 24 hours, creating the cycle of day and night, and that it wobbled slightly over long periods, which helped explain changes in the orientation of the sky. This was a radical shift. If Copernicus was right, then Earth was not the cosmic anchor, but a moving body, part of a larger system. His model explained the apparent backward loops of planets like Mars, known as retrograde motion, more simply than Ptolemy's epicycles. In the heliocentric model, retrograde motion happened naturally because Earth, moving faster in its orbit, would overtake outer planets, making them appear to move backward against the background stars. However, Copernicus still assumed that planets moved in perfect circles, an idea rooted in centuries of philosophical belief that circles were the most divine shape. Because of this, his model wasn't significantly more accurate at predicting planetary positions than Ptolemy's system. Still, conceptually, it was a revolutionary shift. Earth was no longer the center. The next major blow to the geocentric worldview came from Galileo Galilei in the early 1600s. Galileo did not invent the telescope, but he improved it and used it systematically to study the sky. What he observed directly contradicted the old ideas of a perfect Earth-centered cosmos. When Galileo turned his telescope on the moon, he saw craters and mountains. The moon was not a flawless heavenly body, but a world with imperfections similar to Earth. Looking at Jupiter, Galileo noticed 4 small points of light near the planet. Over several nights, he observed them change position, but they always stayed close to Jupiter. These were moons, orbiting Jupiter, not Earth. This discovery proved that not everything in the universe revolved around our planet. Perhaps Galileo's most decisive observation was of Venus. He noticed that Venus went through phases, just like the moon. At times it appeared as a crescent, at others nearly full. This could only be explained if Venus orbited the Sun. If Venus circled Earth, it would not show the full range of phases. Galileo's evidence strongly supported Copernicus's heliocentric model. These discoveries challenged centuries of belief. The Church, which had long supported the geocentric system, opposed Galileo's claims. He was eventually tried by the Inquisition and placed under house arrest. But the evidence could not be ignored forever. The telescope had opened a new window into the universe, and what it revealed made it increasingly clear that Earth was not the center. While Galileo was gathering evidence, Johannes Kepler was working on the mathematics of planetary motion. Using the precise observations collected by his mentor, Tycho Brahe, Kepler spent years trying to fit the data into the Copernican system. He struggled because Copernicus had Euclid's circular orbits. Eventually, Kepler realized that the data only made sense if the planets moved in ellipses, not circles. This breakthrough became Kepler's first law. Planets move in elliptical orbits, with the Sun at one focus. His second law stated that a line connecting a planet to the Sun sweeps out equal areas in equal times, meaning planets move faster when they are closer to the Sun and slower when they are farther away. His third law established a relationship between the time a planet takes to orbit the Sun and its distance from the Sun. The square of the orbital period is proportional to the cube of its average distance. These 3 laws accurately describe planetary motion without the need for epicycles or complicated adjustments. They provided a framework that supported the heliocentric model with precise mathematics. The final piece of the puzzle came with Isaac Newton in the late 1600s. Newton asked the question, why do planets move the way Kepler described? Why don't they fly off into space or fall into the Sun? His answer was the law of universal gravitation. Newton showed that every object with mass attracts every other object with mass. The strength of this force depends on the masses involved and the distance between them. With this law, Newton connected the motion of falling apples on Earth to the orbit of the Moon and the paths of planets. Gravity, acting over vast distances, was the invisible force that kept planets in orbit around the Sun. Newton's laws of motion and gravitation unified the heavens and Earth under the same principles, something never achieved before. By the end of the 17th century, the shift was complete. Earth was no longer the fixed center of the universe. It was a planet spinning on its axis and orbiting the Sun, subject to the same physical laws as everything else in the cosmos. The geocentric model had been replaced by a heliocentric one supported by observation, mathematics, and physical law. This change was more than a scientific correction. It was a philosophical transformation. Humanity was no longer at the center of creation. Earth was just one world among many, moving through space according to universal laws. The spotlight had shifted from Earth to the Sun, but even that wouldn't last forever. As later discoveries would show, the Sun itself is not stationary, nor is it the center of all things. It is simply one star in a vast galaxy, itself in motion. Even with all this knowledge, we still experience the same illusion as the ancients. The ground feels solid, the sky appears fixed, and motion is invisible to us. We don't sense Earth spinning at over 1,600 kilometers per hour or orbiting the Sun at 107,000 kilometers per hour. We don't notice the Sun carrying us along as it moves through the galaxy. Our senses give us the same impression of stillness that fooled early civilizations. But thanks to Copernicus, Galileo, Kepler, and Newton, we know better. The Earth is not special, not central, and not still. It is part of a dynamic system of motion governed by universal laws. The first step in answering where everything in the universe is going was realizing that Earth is going somewhere too. When Earth was removed from the center of the universe, the Sun seemed to take its place. In the heliocentric model, the Sun was the anchor, holding the planets in orbit through the force of gravity. For centuries, it was treated as a fixed reference point, solid, steady, and unmoving. But as astronomers improved their tools and methods, they discovered that the Sun is not still either. Like Earth, it is in constant motion. In fact, the Sun is part of a much larger journey, carrying the entire solar system with it. In the 18th century, the German-born astronomer William Herschel played a central role in uncovering the Sun's movement. Herschel was originally a musician, but his passion for building telescopes led him into astronomy. With the powerful instruments he crafted, Herschel began a systematic survey of the night sky. He and his sister Caroline counted stars in narrow strips, recording their positions and brightness. This method allowed him to build one of the first maps of the Milky Way. Herschel concluded that the stars were not scattered randomly, but formed a flattened system, what we now recognize as the Milky Way galaxy. He also realized that the Sun was not at rest within this system. By studying the apparent motion of nearby stars, he suggested that our solar system was drifting through space in a specific direction. Though his measurements were limited by the technology of his time, he had made a profound discovery: the Sun itself was moving. In the 19th century, astronomers like Friedrich Bessel and later Jacobus Kapteyn improved on Herschel's ideas. They studied the proper motion of stars, the tiny shifts in a star's position against the background sky over many years. These shifts are extremely small, but with precise measurements and careful calculations, astronomers could use them to infer the Sun's motion relative to its stellar neighbors, Ka. Kapteyn's work in particular revealed patterns in the movements of stars. They did not drift in random directions. Instead, their motion suggested that the Sun was traveling toward a specific point in the sky. This point is now called the solar apex, located near the constellation Hercules. By analyzing star catalogues from observatories around the world, Kapteyn estimated that the Sun was moving at roughly 20 kilometers per second relative to nearby stars. Later, more accurate measurements revised this speed upward, but his conclusion remained correct: the Sun is not stationary. As our understanding of the Milky Way improved, it became clear that the Sun is orbiting the center of the galaxy. The Milky Way is a massive spiral system containing hundreds of billions of stars, along with gas, dust, and dark matter. All of this material is held together by gravity. Just as Earth orbits the Sun orbits the galaxy's center. This galactic orbit is enormous. The Sun is located about 27,000 light-years from the center of the Milky Way. At this distance, it takes about 225 to 250 million years to complete a single orbit. That means during Earth's 4.5 billion year history, the solar system has circled the galaxy roughly 20 times. The last time the Sun was in its current position, dinosaurs had just begun to appear on Earth. The Sun travels at an astonishing speed, more than 200 kilometers per second, or about 720,000 kilometers per hour, yet we don't notice this motion because everything around us, including Earth and the other planets, shares it. Once again, motion is relative. To an observer outside the galaxy, the Sun is racing through space, but from our perspective, it feels still. The Sun's orbit is not a simple circle. It wobbles slightly, moving above and below the plane of the galaxy as it travels. It also drifts inward and outward to some degree. Along the way, it passes through regions with varying densities of stars and interstellar gas. Some scientists have suggested that these passages might influence conditions on Earth, perhaps by disturbing comets in the outer solar system or affecting the amount of cosmic radiation that reaches us. Though these ideas remain under investigation, they remind us that the Sun's galactic journey is not entirely smooth. Our solar system is also part of a larger group of stars moving together. The Sun belongs to a collection called the local standard of rest, which is essentially the average motion of stars in our part of the Milky Way. By comparing the Sun's velocity to this standard, astronomers refine their measurements of its true motion. At the heart of the Milky Way lies a supermassive black hole known as Sagittarius A. It contains more than 4 million times the mass of the Sun, compressed into a region smaller than our solar system. Though it does not dominate the galaxy by itself, it plays a central role in anchoring the Milky Way's structure. The Sun and every other star in the galaxy are ultimately orbiting around this gravitational center. This discovery underscored a larger point. Even the Sun, which once seemed like the ultimate reference point, is just another star bound to the dynamics of the galaxy. It is not central and it is not still. It is one participant in the enormous dance of billions of stars. The realization that the Sun is in motion further dismantled the old idea of a static universe. First, Earth was removed from the center. Then the Sun lost its role as the fixed anchor of the cosmos. Each step revealed that the universe is far more dynamic than it appears. The motions you don't feel the spin of Earth, its orbit around the Sun's orbit around the galaxy, add up to an extraordinary journey through space. To put this in perspective, consider the distances involved. In the time it takes you to read this paragraph, the Sun has traveled hundreds of kilometers through the galaxy. Over the course of a human lifetime, the solar system covers trillions of kilometers along its galactic path, yet the stars around us remain so far away that the patterns of constellations barely change. Only with precise instruments and long-term observations can we detect the Sun's true motion. Today, astronomers continue to refine their measurements of the Sun's movement using advanced tools like the Gaia Space Observatory, which is mapping the positions and motions of more than 1 billion stars. These data give us the most detailed picture yet of the solar system's path through the Milky Way. They also help us understand the galaxy's structure, rotation, and gravitational forces. The story of the Sun's motion is a reminder that no object in the universe is isolated. Everything is connected by gravity and part of larger patterns of movement. The Sun carries us around the Milky Way just as Earth carries us around the Sun. This chain of motion extends outward to the galaxy itself, which is also not standing still. And that leads to the next step in our journey. If the Sun and the solar system are in motion around the galaxy, what about the galaxy itself? Where is the Milky Way going? The answer opens up an even bigger perspective on the universe's constant flow. For a long time, astronomers thought the Sun might be near the center of the galaxy. After all, early surveys suggested the stars around us were spread in all directions with no obvious sign of where the middle might be. But as observations improved, it became clear that the Milky Way has a structure, and at its heart lies something extraordinary. The story of how we discovered the true center of our galaxy is one of the most important chapters in our understanding of cosmic motion. In the late 18th century, William Herschel used star counts to create one of the first maps of the Milky Way. He concluded that the galaxy was shaped like a flattened disk, and that the Sun was located roughly near the center. This was a reasonable conclusion, since interstellar dust blocked distant stars from view, making the distribution look more balanced than it really was. For over a century, astronomers built models based on incomplete data, and most of them placed the Sun somewhere near the middle. By the early 20th century, however, evidence was beginning to suggest otherwise. Jacobus Kapteyn proposed a model of the Milky Way that again put the Sun near the center, but like Herschel, he underestimated the effects of interstellar dust. As a result, his map made the galaxy appear much smaller than it really is. It took new methods of observation to reveal the truth. A breakthrough came from the work of American astronomer Harlow Shapley in the 1910s. Shapley studied globular clusters, dense groups of hundreds of thousands of stars that orbit the galaxy. He realized that these clusters were not spread evenly across the sky. Instead, they formed a pattern that pointed to a center far from the Sun, in the direction of the constellation Sagittarius. By measuring the distances to these clusters using variable stars known as Cepheids, Shapley estimated the true scale of the Milky Way. His results showed that the galaxy was far larger than previously thought, and that the Sun was located well away from the center, about 25,000 light-years out. This was another blow to the idea of our central importance. First, Earth had been dethroned, then the Sun, and now even our position in the galaxy was revealed to be off-center. As astronomers studied the motions of stars, they noticed something surprising. Stars near the center of the galaxy orbited at very high speeds. According to Newtonian mechanics, the amount of visible mass, stars, gas, and dust, wasn't enough to account for these high velocities. Something massive and invisible had to be generating the necessary gravitational pull. This hidden mass hinted at the existence of a dense object at the galaxy's core. For decades, the nature of this object remained uncertain. Some proposed it was simply a dense cluster of stars. Others suggested it might be something more exotic. In the mid-20th century, radio astronomy opened a new window into the Milky Way. Unlike visible light, radio waves can pass through the dust that obscures our view of the galaxy's center. Using radio telescopes, astronomers detected a strong source of radio emission in the direction of Sagittarius. This source, discovered in 1974, was named Sagittarius A. Sagittarius A didn't look like much in visible light, but in radio wavelengths it was bright and compact. Over time, increasingly precise observations revealed that stars near the galactic center were orbiting an invisible object with astonishing speed. Some of these stars completed orbits in just a few years, whipping around a point that emitted almost no visible light. By tracking these stars, astronomers were able to calculate the mass of the central object. The results were staggering. It contained about 4 million times the mass of the Sun, packed into a region smaller than our solar system. The only object that fit these properties was a supermassive black hole. The confirmation of a supermassive black hole at the heart of the Milky Way marked a major milestone in astronomy. This object, Sagittarius A, anchors the orbits of the stars in the central region and plays a key role in the dynamics of the galaxy as a whole. It doesn't actively consume large amounts of material at the moment, so it is relatively quiet compared to black holes in some other galaxies, but its gravity dominates the core of the Milky Way. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A, produced by combining data from radio telescopes across the globe. The image showed a glowing ring of hot gas surrounding a dark central shadow, the black hole itself. This direct visual evidence confirmed decades of indirect measurements. Our Sun, along with the entire solar system, orbits this central black hole at a distance of about 27,000 light-years. The orbit takes roughly 225 to 250 million years to complete. This means that since the formation of Earth, the solar system has circled the galactic center around 20 times. During that time, the galaxy itself has evolved, with new stars forming, old ones dying, and spiral arms shifting their structure. The Sun's orbital speed around the galactic center is about 220 kilometers per second, or nearly 800,000 kilometers per hour. At that velocity, the solar system covers enormous distances every minute, though we remain unaware of it because everything around us shares the same motion. The discovery of the supermassive black hole at the Milky Way's heart reinforced an important lesson. The structures we once considered central and stable are themselves part of larger, dynamic systems. The Sun is not stationary, but bound in orbit around an object we cannot see directly. Our entire planetary system is participating in a journey that spans hundreds of millions of years. This Undii. Understanding also connected the Milky Way to other galaxies. Observations revealed that many, if not most galaxies, harbor supermassive black holes at their centers. Some of these black holes are millions or even billions of times more massive than the one in our galaxy. In active galaxies, material falling into these black holes releases enormous amounts of energy, outshining all the stars combined. Sagittarius A is relatively quiet today, but it may have been more active in the past and could flare up again if it encounters new material to consume. With each step in our understanding, the role of Earth and the Sun became smaller in the grand picture. We are not at the center of the universe, not at the center of the solar system, and not even at the center of our own galaxy. Instead, we orbit a supermassive black hole alongside hundreds of billions of other stars. This realization is humbling, but it also expands our sense of connection to the cosmos. The same gravitational laws that keep Earth in orbit around the Sun also keep the Sun in orbit around the galactic center. The chain of motion extends from the scale of apples falling from trees to the orbits of entire galaxies. The study of the Milky Way's center continues to advance. Instruments like the Very Large Telescope in Chile and the Gaia spacecraft are tracking the motions of stars with incredible precision, giving us new insights into the structure of the galaxy and the influence of Sagittarius A. These observations not only confirm our current models, but also help us refine our understanding of gravity, stellar dynamics, and black hole physics. Knowing that a black hole sits at the center of our galaxy changes the way we think about cosmic motion. The Sun is not circling an abstract point in space, it is orbiting a real, massive object that shapes the destiny of everything in the Milky Way. But even this is the final layer of motion. Just as Earth orbits the Sun and the Sun orbits the galaxy, the Milky Way itself is moving, and that motion carries us into the next chapter of our story. For centuries, the Milky Way was thought to be the entire universe. When people looked up at the night sky, they saw countless stars, but they assumed all of them belonged to a single cosmic system. The faint, cloudy patches seen through telescopes were called nebulae and were believed to be clouds of gas or clusters of stars within our galaxy. The idea that there could be entire other galaxies, vast star systems like the Milky Way, was almost unthinkable. That changed in the early 20th century, when astronomers finally realized that the universe was far larger than anyone had imagined. In the late 19th and early 20th centuries, astronomers were divided about the nature of nebulae. Some believed they were island universes, star systems far beyond the Milky Way. Others thought they were much closer, simply objects within our galaxy. The question became known as the Great Debate. The answer would determine whether the Milky Way was the entire cosmos or just one of many galaxies in a much larger universe. One of the most important nebulae under discussion was the Andromeda Nebula, a faint, elongated patch visible even to the naked eye under dark skies. Through telescopes, it looked like a spiral of light, but nobody knew how far away it was. If it was within the Milky Way, it had to be relatively small. If it was outside, it had to be unimaginably large. The breakthrough came thanks to Henrietta Swan Leavitt, an astronomer working at the Harvard College Observatory. While studying variable stars known as Cepheids, she discovered that the period of their brightness variations was directly related to their intrinsic luminosity. This meant that by observing how long a Cepheid took to brighten and dim, astronomers could calculate how bright it truly was. Comparing this to how bright it appeared allowed them to measure its distance. Leavitt's discovery provided a COSM, IC measuring stick, the first reliable way to calculate distances to faraway stars and galaxies. In the 1920s, Edwin Hubble used the powerful Hooker telescope at Mount Wilson Observatory in California to study the Andromeda Nebula. He identified Cepheid variables within it and calculated their distances. The result was astonishing. Andromeda was far outside the Milky Way, more than 2 million light-years away. This meant it was not a nebula within our galaxy, but an entirely separate galaxy, comparable in size to the Milky Way itself. Hubble's discovery settled the debate. The Milky Way was not the whole universe. It was just one galaxy among many. The cosmos was vastly larger than people had imagined, containing countless galaxies spread across space. Galaxies are enormous systems of stars, gas, dust, and dark matter bound together by gravity. The Milky Way contains roughly 100 to 400 billion stars. Andromeda is similar in size, perhaps slightly larger. Spiral galaxies like these are characterized by their disc-shaped structure, with spiral arms winding outward from a central bulge. Other galaxies take different forms, such as elliptical galaxies that appear as smooth, featureless ovals, or irregular galaxies with no defined shape. Galaxies range in size, from dwarfs with only a few million stars to giants with trillions. They often cluster together in groups and superclusters, forming a cosmic web that spans the observable universe. Hubble's discovery showed that Earth's place in the cosmos was even less central than previously thought. Not only was Earth not the center of the solar system, and the solar system not the center of the Milky Way, but even the Milky Way itself was just one among billions of galaxies. Hubble's work did not stop with proving the existence of other galaxies. By studying their light, he also discovered that most galaxies were moving away from us. Their light was redshifted, meaning its wavelength had been stretched, consistent with the galaxies receding at high speeds. Even more surprising, the farther away a galaxy was, the faster it seemed to be moving away. This relationship, now known as Hubble's law, revealed that the universe itself was expanding. The galaxies were not flying apart through space, rather space itself was stretching, carrying galaxies with it. This discovery transformed cosmology and provided the foundation for the Big Bang theory. The Milky Way is not isolated. It belongs to a small group of galaxies called the Local Group, which includes about 80 members. The two largest are the Milky Way and Andromeda, followed by the Triangulum Galaxy, M33, and many smaller dwarf galaxies, such as the Magellanic Clouds. The Local Group spans about 10 million light-years across and is bound together by gravity. Andromeda and the Milky Way are the dominant members of this group. Their mutual gravitational attraction means they are not drifting apart like more distant galaxies. Instead, they are on a collision course, moving toward each other at roughly 110 kilometers per second. In about 4 to 5 billion years, they will merge to form a single, larger galaxy. The realization that galaxies exist beyond the Milky Way expanded the scale of the universe by orders of magnitude. What once seemed vast, the Milky Way itself, was revealed to be just one small part of a much larger structure. It was as if humanity had thought its hometown was the entire world, only to suddenly discover an entire planet filled with cities, continents, and oceans. This new perspective also changed how we view motion in the cosmos. The Sun is not only orbiting the center of the Milky Way itself is moving relative to other galaxies. The local group drifts through space, pulled by the gravity of larger clusters and superclusters. Motion exists on every scale, from planets around stars to galaxies within the cosmic web. Beyond their role in reshaping our view of the universe, galaxies also serve as natural laboratories for studying cosmic evolution. By observing galaxies at different distances, astronomers can look back in time, since light from distant galaxies has traveled for billions of years before reaching us. This allows scientists to study how galaxies formed and evolved over cosmic history. Some galaxies appear calm, with steady star formation, while others are violent and chaotic, with bursts of activity fueled by collisions and mergers. Central black holes, star formation rates, and the distribution of dark matter all play roles in shaping their structure. By studying galaxies beyond the Milky Way, astronomers gain insight into the processes that have also shaped our own galaxy. The discovery of galaxies beyond the Milky Way was a turning point. It showed that the universe is not a static backdrop of stars, but a vast dynamic system of galaxies in motion. Each galaxy, including our own, is part of a larger story of expansion and evolution. As we continue this journey, the next question becomes, if galaxies are moving, what paths are they following? Where is the Milky Way headed? And what forces are shaping its trajectory? The answer leads us to an even larger scale, the expanding universe and the ultimate fate of cosmic motion. When astronomers first realized that the Milky Way was just one galaxy among many, the next natural question was, how are all these galaxies arranged, and how do they move? At the start of the 20th century, many scientists still imagined the universe as a giant but static system. Galaxies might drift slightly, but the overall structure was thought to be stable and eternal. This view made sense based on human experience. After all, the stars in the sky seemed fixed and unchanging. But careful observation soon revealed that the universe was not static at all. Instead, it was expanding. The story began in the 1910s with Vesto Melvin Slipher, an American astronomer at the Lowell Observatory. Slipher studied the light from spiral nebulae, which we now know are galaxies. He analyzed their spectra, the spread of light into different wavelengths, and discovered that many of these objects showed a shift toward the red end of the spectrum. This red shift meant the galaxies were moving away from us. Slipher's work was the first hint that the universe might not be static, but his results were not widely understood at the time. In the 1920s, Edwin Hubble built on Slipher's findings. Using the Hooker telescope, he measured the distances to many galaxies by identifying Cepheid variable stars within them. Thanks to Henrietta Leavitt's earlier discovery of the Cepheid period luminosity relation, Hubble could calculate how far away these galaxies were. When he compared their distances to their redshifts, he noticed a striking pattern. The farther a galaxy was, the faster it seemed to be receding. This relationship, now called Hubble's law, revealed a profound truth. Galaxies were not just moving away at random, their speeds increased with distance in a consistent way. The simplest explanation was that space itself was expanding, carrying galaxies with it. The universe was not it was dynamic, growing larger over time. To understand this concept, it helps to use an analogy. Imagine a loaf of raisin bread rising in the oven. As the dough expands, the raisins inside move farther apart. Importantly, no raisin is the center of the expansion. From the perspective of each raisin, all the others appear to be moving away. In the same way, galaxies are not flying through empty space away from a single central point. Instead, space itself is stretching, increasing the distance between galaxies everywhere. This was a radical shift in perspective. For centuries, people had pictured the universe as eternal and unchanging. Now evidence showed it had a history. If the universe was expanding today, then in the past it must have been smaller, denser, and hotter. This realization laid the foundation for the idea of the Big Bang, the explosive beginning of cosmic expansion. Interestingly, Albert Einstein had predicted something similar in his equations of general relativity. His theory showed that the fabric of space-time is influenced by mass and energy, and that the universe could not remain perfectly static. Either it had to expand or contract. But at the time, most scientists believed the universe was eternal and unchanging, so Einstein added a cosmological constant to his equations to force a static solution. When Hubble's discovery of expansion became known, Einstein reportedly called his cosmological constant the biggest blunder of his life. Ironically, decades later, a form of the cosmological constant would return in the form of dark energy. But in the 1930s, Hubble's observations alone were enough to prove that Einstein's original equations predicting expansion had been correct. In the 1960s, further evidence cemented the idea of an expanding universe with a hot origin. Two radio engineers, Arno Penzias and Robert Wilson, accidentally discovered a faint background signal of microwave radiation coming from every direction in the sky. This signal turned out to be the cooled remnant of the radiation released when the universe was only 380,000 years old. Known as the Cosmic Microwave Background (CMB), it provided direct proof that the universe began in a hot, dense state and had been expanding and cooling ever since. The discovery of the CMB confirmed the Big Bang model and showed that expansion was not just a local phenomenon, but a universal one. Galaxies were moving apart because the universe itself was stretching. Hubble's original estimate of the rate of expansion, known as the Hubble constant, was too high because distance measurements at the time were not precise. Today, using modern telescopes and satellites, astronomers can measure this value much more accurately. The Hubble constant is now known to be about 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years, 1 megaparsec of distance, a galaxy recedes 70 kilometers per second faster. However, there is still debate. Different methods of measuring the Hubble constant give slightly different results, and this discrepancy, called the Hubble tension, is one of the big puzzles in modern cosmology. It may even point to new physics beyond our current understanding. The expansion of the universe is not slowing down. In fact, in 1998, two independent teams of astronomers discovered that it is accelerating. By studying distant supernovae, they found that galaxies are receding faster than expected. This surprising result implied that some unknown force, now called dark energy, is driving the acceleration. Dark energy appears to make up about 70% of the total energy content of the universe, dominating its fate. This discovery had profound implications for the future. If expansion is accelerating, then distant galaxies will move beyond our observable horizon. Over billions of years, only galaxies in our local group like Andromeda and the Milky Way will remain visible. Everything else will fade from view as the fabric of space stretches faster than light can travel. The recognition that the universe is expanding transformed science. It turned the cosmos into a story with a beginning, a present, and a future. It connected the motions of galaxies to the laws of physics governing space and time. It showed that the universe is not static but dynamic, evolving on timescales far beyond human experience. Every galaxy we observe, from spirals like the Milky Way to giant ellipticals, is participating in this expansion. The light we see from distant galaxies is stretched on its journey, carrying with it a record of the universe's growth. Each observation of redshift is a measurement of cosmic history in motion. What began with faint shifts in spectral lines measured by Vesto Slipher has become one of the cornerstones of modern cosmology. The universe is expanding, and the farther we look, the faster galaxies appear to recede. The discovery reshaped our understanding of reality itself, proving that the cosmos is not fixed, but in constant transformation. The next chapter in our journey asks, if the universe is expanding and galaxies are receding from one another, what happens when two galaxies are close enough for gravity to overcome expansion? In our case, the answer is already written in the stars. The Milky Way and Andromeda are on a collision course, and their eventual merger will dramatically reshape our cosmic neighborhood. When astronomers discovered that the universe is expanding, it seemed to imply that all galaxies were moving away from each other. In general, that is true. The more distant a galaxy is, the faster it recedes. But not every galaxy is carried outward by expansion in the same way. On smaller scales, gravity can overpower the stretching of space. That's exactly what's happening with our nearest large neighbor, the Andromeda Galaxy. Instead of drifting farther away, Andromeda is on a direct collision course with the Milky Way. The Andromeda Galaxy, also known as M31, is a massive spiral galaxy located about 2.5 million light-years away. It is the largest member of the local group, which also includes the Milky Way, the Triangulum Galaxy, M33, and dozens of smaller dwarf galaxies. Andromeda is similar in structure to the Milky Way, with a central bulge, a disk of stars, and well-defined spiral arms. It contains around 1 trillion stars, about twice as many as the Milky Way, and spans more than 220,000 light-years across. Because of its size and relative closeness, Andromeda is one of the few galaxies visible to the naked eye under dark skies. For centuries, it was thought to be just another nebula within our galaxy, until Edwin Hubble proved in the 1920s that it was far beyond the Milky Way, an independent galaxy in its own right. Now we know it is also our future partner in a galactic merger. Most galaxies show redshift, meaning they are moving away. Andromeda, however, shows a blue shift. Its light waves are compressed, indicating it is moving toward us. Early measurements suggested this unusual motion, but more recent and precise data from instruments like the Hubble Space Telescope and the Gaia spacecraft have confirmed it. Andromeda is approaching at about 110 kilometers per second, or more than 400,000 kilometers per hour. This approach does not contradict the expansion of the universe. On small scales, gravity dominates over expansion. The mutual gravitational pull of the Milky Way and Andromeda has locked them into a bound system, and they are closing the gap between them. Although Andromeda is moving toward us quickly, space is vast. At its current distance of 2.5 million light-years, the collision won't occur for about 4 to 5 billion years. That sounds unimaginably far in the future, but on cosmic timescales, it is relatively soon. By the time the galaxies meet, the Sun will be nearing the end of its life, transforming into a red giant and eventually shedding its outer layers. The first close pass between the Milky Way and Andromeda will likely occur in about 4 billion years. The galaxies will stretch and distort each other through gravitational tidal forces, flinging out long streams of stars. After the first encounter, they will swing past each other, then be drawn back together for another pass. Over time, their mutual gravity will slow them down and pull them into a final merger. The entire process will take several billion years to complete. The term collision may suggest catastrophic impacts between stars, but that is not the case. Stars are so far apart that the likelihood of two colliding is extremely low, even in the dense cores of galaxies. To put it in perspective, if a star were the size of a ping-pong ball, its nearest neighbor would typically be hundreds of kilometers away. During the merger, stars will pass by one another without direct contact. The real drama occurs in the structure of the galaxies. Gravity will distort their spiral arms, creating tidal tails, long streams of stars pulled away into space. Gas clouds will collide, compressing and triggering bursts of new star formation. Some stars, especially those in the outer regions, may be flung out entirely, cast into intergalactic space. Others will be drawn inward, changing their orbits as the galaxies combine. The central black holes of the Milky Way and Andromeda will eventually spiral toward each other, merging into an even larger supermassive black hole at the heart of the new galaxy. This event could release enormous amounts of energy in the form of gravitational waves. If any humans or human descendants are still around in 4 billion years, the night sky will look dramatically different. As Andromeda approaches, it will grow larger and brighter, eventually dominating the sky with its spiral arms. Over time, the two galaxies will appear to merge into a distorted, chaotic shape before settling into a new form. Simulations suggest that the final result will be an elliptical galaxy, larger, rounder, and more diffuse than either spiral. Astronomers have even given this future galaxy a name, Milkomeda or Milkdromeda, a combination of the Milky Way and Andromeda. It will be a giant elliptical galaxy with hundreds of billions, perhaps trillions of stars. Our Sun, if it still exists, will have moved to a new orbit within this merged system, far from where it is today. The merger of the Milky Way and Andromeda will reshape the local group as a whole. Smaller galaxies like the Triangulum Galaxy may be drawn into the collision, either merging with the new giant or becoming satellites. The gravitational influence of the merged galaxy will dominate the local group, transforming it into a single massive system. On a larger scale, however, this event is relatively common. Galaxies merge frequently in the history of the universe. Many of the elliptical galaxies we observe today are the products of past collisions. Our future merger with Andromeda is just part of the natural process of galactic evolution. The Andromeda collision highlights a key principle of cosmic motion. Gravity shapes structures on every scale. While the universe expands overall, local systems of galaxies are bound together. Within those systems, galaxies orbit, interact, and merge, creating the diverse structures we observe. For the Milky Way, the collision with Andromeda is not an end, but a transformation. The stars will continue to orbit within the merged galaxy. New stars will form from colliding gas clouds, and the supermassive black hole at the center will grow larger. Life on Earth may not survive to witness it, but the cosmic journey will continue. Understanding the future collision with Andromeda also prepares us to consider even larger scales of motion. The local group itself is not stationary. It is moving toward other groups and clusters, drawn by vast structures of galaxies and dark matter. Just as Earth orbits the Sun orbits the Milky Way, and the Milky Way is bound to Andromeda. Our entire local group is part of a flow of galaxies shaped by even greater forces. The next chapter in our exploration will take us beyond the local group into the realm of galaxy clusters, superclusters, and mysterious attractors. There we find that not only are galaxies merging locally, but entire regions of the universe are being pulled and stretched on a scale almost beyond comprehension. When astronomers realized that the universe is expanding, it seemed like everything was moving away from everything else in a uniform pattern. On the largest scales, this is true, but as observations became more precise, scientists noticed that galaxies do not simply follow the expansion. Some regions of the cosmos show strange, large-scale flows of galaxies, where thousands of them appear to be drifting in the same direction, as if pulled by an unseen hand. One of the most intriguing examples of this phenomenon is the so-called Great Attractor. The Milky Way and Andromeda dominate our local group, but this group itself is not at rest. By studying the motions of galaxies using redshift measurements, astronomers discovered that the local group is moving relative to the cosmic microwave background, the faint afterglow of the Big Bang. This motion is significant, about 600 kilometers per second, or over 2 million kilometers per hour. The question immediately arose: what could be pulling such a massive group of galaxies at that speed? To answer this, astronomers had to study not just the local group, but also the larger structures of which it is a part. Our local group belongs to a cluster of galaxies called the Virgo cluster, which in turn is part of a much larger structure called the Laniakea supercluster. This vast region spans more than 500 million light-years and contains around 100,000 galaxies. Within this web of cosmic structures, gravitational forces are not evenly distributed. Some regions contain more matter, both visible and dark, than others. These overdense regions act like gravitational wells, drawing galaxies toward them. In the 1970s and 1980s, astronomers mapping the motions of galaxies noticed something unusual. Many galaxies in the local universe, including the Milky Way, appeared to be drifting toward a region in the direction of the constellations Centaurus and Hydra. This region was later named the Great Attractor. The problem was that the Great Attractor lies behind the plane of the Milky Way, in a region of the sky heavily obscured by dust and gas. This zone of avoidance, as astronomers call it, makes direct observations difficult. Nevertheless, indirect measurements indicated that a huge mass concentration was present there, exerting gravitational influence over hundreds of millions of light-years. Early estimates suggested that the Great Attractor had a mass equivalent to tens of this ousans of Milky Way galaxies. However, further study revealed that it is not a single object, but part of a larger concentration of galaxies. At its core lies the Norma cluster, a dense collection of galaxies about 200 million light-years away. The combined mass of this cluster and the surrounding structures creates a gravitational center pulling in galaxies, including our own. This pull explains part of the local group's motion. Our galaxy is not just drifting randomly, but is being drawn toward this overdense region. Yet the story does not end there. Beyond the Great Attractor lies an even larger structure, the Shapley supercluster, which may also contribute to the flow of galaxies in this direction. The motion we observe is therefore the result of multiple massive structures tugging on us simultaneously. To place this in context, In 2014, astronomers mapped the large-scale motions of thousands of galaxies and redefined the boundaries of our supercluster. They named it Laniakea, meaning immense heaven in Hawaiian. Laniakea is not bound in the way a galaxy cluster is, but is defined by the flow of galaxies toward a common region, the Great Attractor. In other words, Laniakea is the region of space in which galaxies, including the Milky Way, are all moving toward the same gravitational basin. This view transformed our understanding of cosmic geography. Just as rivers flow downhill toward valleys, galaxies flow through space toward gravitational centers. The Great Attractor is the valley floor in our region of the universe, and we are one of the countless galaxies moving along the slopes toward it. Interestingly, the motion of the local group is not just explained by attraction. In recent years, astronomers have proposed the existence of something called the dipole repeller, a vast region of unusually low density in the opposite direction of the Great Attractor. Just as dense regions pull galaxies in, underdense regions push them away. The combined effect of being pulled by the Great Attractor and pushed by the dipole repeller helps explain the observed motion of the local group relative to the cosmic microwave background. This highlights an important concept. Motion on cosmic scales is not caused by single objects alone, but by the balance of forces from multiple structures. Galaxies are influenced by a network of attractions and repulsions across hundreds of millions of light years. The ultimate fate of our journey toward the Great Attractor is uncertain. Because the universe is expanding at an accelerating rate due to dark energy, the pull of gravity may never fully overcome the outward push of expansion on the largest scales. This means that while we and our neighboring galaxies are drifting toward the Great Attractor now, the accelerating expansion of space may eventually isolate us, preventing us from ever reaching it. In the nearer future, on timescales of billions of years, the Milky Way's collision with Andromeda will dominate our local cosmic story. Together, the merged galaxy will continue its drift within Laniakea, part of the slow-motion river of galaxies flowing toward the Norma cluster and beyond. The Great Attractor serves as a reminder that our galaxy is not isolated. It is part of an enormous interconnected web of cosmic structures. Just as Earth is not the center of the solar system, and the Sun is not the center of the Milky Way itself is not stationary. It is moving as part of a vast flow of galaxies, shaped by forces on scale that dwarf even our galaxy. For humanity, these discoveries are humbling. They reveal that our cosmic journey is part of something much larger than we can see with the naked eye. While we may never personally feel the pull of the Great Attractor, our galaxy's trajectory is shaped by it, and our place in the universe is defined by the interplay of structures far beyond our immediate surroundings. As technology improves, astronomers continue to map the universe in greater detail, using radio telescopes, infrared surveys, and space-based observatories to peer through the zone of avoidance. These efforts are gradually revealing the hidden structures around the Great Attractor and clarifying the large-scale flows of galaxies. Each discovery adds to our picture of a universe in motion, where nothing stands still and every object is part of a vast, interconnected dance. The story of the Great Attractor prepares us for the final step in our journey, considering not just where galaxies are moving today, but where the universe as a whole is headed. To understand that, we must explore the nature of dark energy and the ultimate fate of cosmic expansion. For most of the 20th century, astronomers assumed that the expansion of the universe, discovered by Edwin Hubble, would gradually slow down over time. The reasoning was straightforward. Gravity, the attractive force between all forms of matter, should act to pull galaxies back together. Even though the universe was expanding, the enormous mass of stars, gas, dust, and dark matter ought to slow the expansion. The open question was whether gravity was strong enough to eventually reverse it and cause a collapse, or whether the universe would keep expanding forever at a decelerating rate. This picture made sense until the late 1990s, when astronomers studying distant supernovae made a shocking discovery. Instead of slowing down, the expansion of the universe was speeding up. Something was pushing galaxies apart with increasing force. That something is what we now call dark energy. The key evidence came from Type Ia supernovae, exploding stars that serve as standard candles. These supernovae occur when white dwarf stars in binary systems accumulate enough material from their companions to trigger runaway nuclear reactions. Because they always explode with roughly the same intrinsic brightness, astronomers can use them to measure distances. In the 1990s, two teams, the Supernova Cosmology Project and the High Z Supernova Search Team, observed dozens of these events in distant galaxies. By comparing their distances to their redshifts, they expected to measure how much the expansion of the universe had slowed. Instead, they found the opposite. The distant supernovae were dimmer than expected, meaning they were farther away than predicted. This implied that the expansion had been accelerating for billions of years. This discovery brought new attention to an old idea. In 1917, Albert Einstein introduced the cosmological constant into his equations of general relativity to allow for a static universe. When Hubble discovered expansion, Einstein abandoned the constant, calling it his biggest blunder. But the supernova results suggested that a form of repulsive energy really does exist, something similar to Einstein's constant, but on a larger scale. Today, cosmologists often describe dark energy as a property of space itself. As space expands, more of this energy comes into existence, driving faster expansion. Unlike gravity, which pulls matter together, dark energy pushes the fabric of the cosmos apart. Measurements of the cosmic microwave background, combined with observations of large-scale galaxy surveys, show that dark energy dominates the universe. Roughly 70% of the total energy content of the cosmos is dark energy. About 25% is dark matter, the invisible material that holds galaxies and clusters together. Ordinary matter, the atoms that make up stars, planets, and people, accounts for less than 5%. This breakdown means that most of the universe is made of things we cannot see directly. The familiar matter that humans have studied for centuries is just a small fraction of reality. Dark matter and dark energy, while mysterious, shape the largest structures and the ultimate fate of the cosmos. Despite its importance, the nature of dark energy remains unknown. There are several leading ideas. One possibility is that dark energy is simply Einstein's cosmological constant, a fixed property of space itself. In this view, space naturally has a small but positive energy that causes expansion to accelerate. Another possibility is that dark energy is a new dynamic field that changes over time, sometimes called quintessence. Unlike the cosmological constant, quintessence could evolve, with its strength increasing or decreasing depending on conditions. A more radical idea is that our understanding of gravity itself is incomplete. Instead of adding dark energy to explain acceleration, some scientists propose modifying Einstein's equations on cosmic scales. These modified gravity theories attempt to explain cosmic acceleration without invoking an unknown form of energy. At present, there is no definitive answer. Dark energy is one of the biggest mysteries in science, comparable to the discovery of heliocentrism or relativity in terms of its potential to reshape our understanding of the universe. To study dark energy, astronomers use several observational tools. One method involves mapping the large-scale distribution of galaxies and looking for patterns known as baryon acoustic oscillations, relics of sound waves from the early universe. These patterns act as a kind of cosmic yardstick to measure how fast the universe has expanded at different times. Another method involves gravitational lensing, the way massive objects bend light. By measuring how dark matter and galaxies distort the light from background galaxies, scientists can infer how structures grow over time. Since dark energy affects the growth of structure, these measurements provide clues about its nature. Future observatories, such as the Euclid mission, already launched in 2023, and the Vera C. Rubin Observatory, are designed to gather enormous data sets to refine our understanding of dark energy. The hope is that more precise measurements will distinguish between a true cosmological constant and alternative explanations. Dark energy doesn't just affect the present, it determines the ultimate fate of everything. Several scenarios are possible, depending on the properties of dark energy. The Big Freeze. If dark energy continues as it is today, the universe will expand forever at an accelerating rate. Over time, galaxies will drift beyond one another's horizons, leaving the local group isolated. Stars will burn out, new star formation will cease, and the universe will become a cold, dark, and empty place. This is currently considered the most likely scenario. The Big Rip. If dark energy grows stronger over time, its repulsive force could eventually overcome all other forces. Galaxies would be torn apart, followed by stars, planets, and even atoms. The universe would end in a catastrophic rip, with space-time itself torn apart. The Big Crunch. If dark energy weakens or reverses, gravity could even chilly wind, expansion would slow, stop, and then reverse, collapsing the universe back into a dense state. This big crunch would be the opposite of the Big Bang. Current evidence suggests this outcome is unlikely, but it cannot be completely ruled out. The bounce or cyclic model. Some theories propose that the universe undergoes cycles of expansion and contraction. In this view, the current expansion might one day reverse into a crunch, followed by another bang. Though speculative, this idea remains a possibility in some models of cosmology. What makes dark energy so profound is that it forces us to admit how little we know about the universe. We can measure its effects with increasing precision, but its true nature is elusive. It could be a simple cosmological constant, a new kind of field, or even a sign that our understanding of fundamental physics is incomplete. Regardless of the details, dark energy tells us that the universe is not just expanding but accelerating, and that acceleration is the key to its future. The galaxies we see today are only temporary companions. Over billions of years, most of them will slip away, leaving us in an isolated island of stars. As we stand on Earth, a tiny planet around an ordinary star, the idea that dark energy will shape the fate of everything can be overwhelming. Yet, it also provides a perspective. Just as Copernicus showed that Earth was not the center of the cosmos, and Hubble showed that the Milky Way was just one galaxy among many, dark energy reveals that even the visible matter in galaxies is only a small piece of the whole story. The next chapter will take us into the implications of this discovery for the ultimate fate of the universe itself. Where is everything in the universe going? The answer depends on dark energy, and though we don't yet know its full nature, we can outline the possible destinies that await. As we have followed the journey of cosmic motion from Earth's rotation to the Sun's orbit around the Milky Way to galaxies drifting across the expanding universe, one question has lingered in the background. Where is all of this going? If the universe is in motion on every scale, then what is the final destination? To answer this, scientists turn to cosmology, the study of the universe as a whole, and what we find is that the ultimate fate of everything depends on the delicate balance between gravity, dark matter, and dark energy. Before the discovery of dark energy, there were two main scenarios for the universe's future. The first was eternal expansion. In this model, the universe would continue expanding forever, but the rate of expansion would slow over time as gravity pulled galaxies back against the outward motion. Galaxies would drift farther apart, stars would eventually die, and the universe would cool into a cold, dark, and lifeless place. The second possibility was collapse. If the universe contained enough matter, then gravity would eventually halt the expansion and reverse it. Galaxies would begin moving closer together, leading to a big crunch. All matter and energy would collapse into a hot, dense state, possibly similar to the conditions of the Big Bang. In some speculative theories, this collapse could even trigger another cycle of expansion, creating an eternal, oscillating universe. These were the options scientists debated for much of the 20th century, but the discovery of accelerating expansion in 1998 changed everything. Dark energy now appears to dominate the fate of the universe. With nearly 70% of the cosmos made of this mysterious force, its behavior determines how expansion will proceed. Three major scenarios are most often considered today: the Big Freeze, the Big Rip, and less likely the Big Crunch. The most widely accepted outcome is the Big Freeze, also called heat death. In this scenario, dark energy continues to act as a cosmological constant, a steady property of space that keeps accelerating expansion at its current pace. As billions and trillions of years pass, galaxies will move farther apart. Eventually, all galaxies outside the local group will disappear beyond our cosmic horizon, receding faster than the speed of light due to the expansion of space. Observers in the far future will see only the stars of their own merged galaxy, Milky, while the rest of the universe will be invisible. Inside galaxies, stars will continue to form for some time, but as gas supplies are used up, star formation will slow and eventually stop. Existing stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will cool and fade. Black holes, the final long-lived structures, will slowly evaporate through a process called Hawking radiation. On timescales of 1,000 years or more, even supermassive black holes will vanish. The universe will become a cold, empty, and featureless place, with particles scattered thinly across an ever-expanding void. This is the heat death of the cosmos, not a fiery end, but a slow fade into darkness. A more dramatic possibility is the Big Rip. This scenario occurs if dark energy is not constant but increases in strength over time. If its repulsive force grows, expansion will accelerate without limit. At first, galaxies will be pulled apart from one another. Then the force will overwhelm the gravity binding stars to galaxies, tearing stellar systems apart. Later, it will overcome the gravity of individual stars and planets. In the final moments, even atoms and subatomic particles will be ripped apart as space itself stretches faster than forces can hold matter together. The timeline of the Big Rip depends on the properties of dark energy. If this scenario is correct, the end of the universe could occur tens of billions of years from now. While it is considered less likely than the Big Freeze, it remains a theoretical possibility. The opposite outcome is the Big Crunch, in which expansion eventually reverses. This would happen if dark energy weakened or changed sign, allowing gravity to take over. Galaxies would slow their recession, halt, and then begin moving closer together. Over time, the universe would contract, becoming hotter and denser. In the final stages, all matter and energy would collapse into a singularity. This scenario could mark the absolute end of the universe, or potentially lead to a new beginning if another expansion followed. Some versions of cosmology suggest cycles of expansion and contraction, with universes reborn endlessly. Currently, observations suggest the Big Crunch is unlikely because the data show that expansion is accelerating, not slowing. But until the true nature of dark energy is understood, we cannot rule it out entirely. Each of these scenarios highlights how dependent the fate of the universe is on dark energy. If it remains constant, the Big Freeze is almost certain. If it strengthens, a Big Rip could occur. If it weakens, a Big Crunch might be possible. Our lack of understanding leaves room for all of these futures. Some scientists also speculate about other exotic possibilities. Quantum effects might create new universes branching off from ours in a multiverse, or entirely new physics could emerge on timescales so long that we cannot yet imagine them. In a sense, the ultimate fate of the cosmos remains one of the biggest open questions in science. It is important to remember that these scenarios play out over timescales far beyond human history. The Earth itself will not last anywhere near as long as the universe. In about 5 billion years, the Sun will expand into a red giant, engulfing or scorching the inner planets. Long before the universe reaches its distant fate, our own solar system will be transformed beyond recognition. Still, thinking about the ultimate destiny of the cosmos changes how we view our place in it. For centuries, humans imagined themselves at the center of a static, eternal universe. Now we know that everything is in motion, from our spinning planet to the expansion of the entire cosmos, and we know that this motion has a direction toward a future that will look very different from the present. The question, where is everything in the universe going, has guided much of modern astronomy. It took us from Earth's rotation to the Sun's orbit, from the Milky Way to the Andromeda collision, and finally to the expanding universe shaped by dark energy. Each discovery removed humanity further from the center, but also gave us a deeper understanding of the vast processes at work. The fate of everything may be cold darkness, violent tearing, or eventual collapse. But whatever the outcome, the journey of discovery has already reshaped our view of reality. We are part of a universe that is alive with motion, governed by forces that extend across billions of light years and trillions of years of time.